Here's something that should genuinely bother you. We have sent rovers to Mars. We have photographed the surface of Pluto, a rock so far away that light takes 5 hours just to reach it. We have mapped the craters of the Moon in extraordinary detail. We have pointed telescopes at galaxies so distant that the light we're seeing left before the Earth even existed. And yet, right here on our own planet, beneath the ocean we've been sailing on for thousands of years, there are places no human being has ever seen, places we haven't even tried to look. About 73% of the ocean floor remains unmapped, unexplored, and unseen. And before you think, oh, that's still progress, consider this. As recently as 2017, it was closer to 94%. We've only begun to scratch the surface. We know more about the surface of Mars than we do about what lies beneath the waves covering 71% of our own world. That's not a poetic exaggeration. That is just the truth. So today we're going to take a trip. And I want to warn you, the deeper we go, the stranger it gets. Let's start with some perspective. Because the scale of the ocean is one of those things that your brain genuinely struggles to hold on to. The ocean covers about 361 million square kilometers of the Earth's surface. If you took every mountain on Earth and stacked them inside the ocean, they would all fit, with room to spare. The average depth of the ocean is around 3,700 meters. That's nearly 4 kilometers of water on average, just sitting above the seafloor. Now, when most of us picture the ocean floor, we probably imagine a flat, sandy, slightly boring stretch of nothing. Maybe some coral, some fish, maybe a shipwreck. The reality is almost insultingly more dramatic than that. The ocean floor has mountain ranges that dwarf the Himalayas. It has volcanic systems stretching for tens of thousands of kilometers. It has canyons that make the Grand Canyon look like a ditch. The mid-ocean ridge, the longest mountain range on Earth, runs for over 65,000 kilometers and sits almost entirely underwater, almost entirely unseen. And then at the very bottom of certain parts of the ocean, there are the trenches. The Mariana Trench in the western Pacific Ocean is the deepest known point on Earth. At its lowest point, a spot called Challenger Deep, the ocean floor sits at roughly 11 kilometers below the surface. Let that sink in for a second. If you took Mount Everest, the tallest mountain on Earth at about 8.8 kilometers high, and dropped it into Challenger Deep, the summit would still be over 2 kilometers underwater. For nearly 60 years after the first descent, only 3 people had ever been to Challenger Deep. 3. In all of human history. More people had walked on the moon than had visited the deepest point in our own ocean. That only began to change in 2019, when explorer Victor Vescovo commissioned a purpose-built submersible called the Limiting Factor, designed to make the trip not once, but repeatedly, like a bus route to the bottom of the world. He dove to Challenger Deep 15 times himself and began taking passengers, scientists, astronauts, researchers. The number of humans who have visited Challenger Deep is now creeping upward, but it is still a vanishingly small group, and the vast majority of the abyss remains as unvisited as it has ever been. So why? Why haven't we explored it more? We can build space rockets, for goodness sake. Why is the ocean still such a mystery? The answer comes down to one simple, brutal fact: pressure. The deeper you go in the ocean, the more water is sitting above you. And all of that water has weight. For every 10 meters you descend, the pressure increases by roughly 1 atmosphere, the same amount of pressure the entire column of air above you is exerting at the surface. By the time you're at Challenger Deep, the pressure is over 1,000 times the pressure at the surface. That's about 1,100 kilograms pressing down on every single square centimeter of whatever you've sent down there. To put that in terms you can feel, It's the equivalent of an elephant standing on your thumbnail. On every thumbnail-sized piece of surface area, simultaneously, across whatever you've sent down there. Designing something that can survive that is extraordinarily difficult and extraordinarily expensive. Most materials simply collapse. Electronics behave differently. Cameras fog. Batteries drain faster. Seals and joints become failure points. The engineering challenges are not small. Space, believe it or not, is in some ways easier to design for. A vacuum is a vacuum. But the deep ocean is actively trying to crush everything you send into it. This is why, as of the early 2020s, we have sent robotic spacecraft to orbit every planet in our solar system, landed on the Moon and Mars, and sent 2 probes beyond the edge of the solar system entirely. And yet the majority of our own ocean floor remains a complete mystery. Now let's actually make the descent. Because the ocean doesn't just drop straight into darkness, it changes layer by layer, and each zone is its own completely different world. The top layer, from the surface down to about 200 meters, is called the sunlight zone, or the epipelagic zone. This is the ocean most of us know. It's warm, it's lit, and it's where the vast majority of ocean life that humans have ever interacted with lives. Dolphins, tuna, sharks, sea turtles, coral reefs. All of this exists within the top 200 meters. Sunlight drives photosynthesis here, which feeds the whole food chain. It's busy, colorful, and familiar. And it represents just a tiny sliver of the ocean's total depth. Below 200 meters, things start to change. The next layer is called the twilight zone, or the mesopelagic zone, and it runs down to about 1,000 meters. Sunlight barely reaches here, just faint, dim flickers of blue. It's cold. The pressure is already significant. And the creatures that live here have started doing something remarkable, making their own light. Bioluminescence. It's one of the most mind-bending phenomena in all of nature. Animals in the twilight zone, fish, jellyfish, squid, shrimp, produce their own light through chemical reactions in their bodies. Some use it to attract prey. Some use it to communicate. Some use it to camouflage themselves against the faint light filtering down from above, so predators looking up can't spot their silhouette. Scientists now estimate that bioluminescence is actually the most common form of communication on Earth. More animals use it than any other method. We just never really noticed because it all happens in the dark, far below the surface. Then we go deeper still. From 1,000 meters to about 4,000 meters is the midnight zone or the bathypelagic zone. No light reaches here at all. None. It is completely, permanently, absolutely dark. The temperature hovers just above freezing. The pressure would kill a human being in an instant. And yet, life is here. The anglerfish lives here. The giant squid lives here. Strange, pale, slow-moving creatures that have adapted over millions of years to a world of total darkness, extreme cold, and crushing pressure. Many of them have enormous eyes, trying to catch any photon of bioluminescent light that might drift by. Others have no eyes at all. What would be the point? Some fish in this zone have developed transparent bodies. Some have mouths that can unhinge to swallow prey larger than themselves, because food is so scarce down here that when you encounter a meal, you cannot afford to let it get away. Below 4,000 meters is the abyssal zone, named after the Greek word for bottomless. This is the vast, flat, cold plain that covers more of the Earth's surface than any other terrain type on the planet. It's pitch dark, near freezing, and under pressures that seem almost incompatible with life. And yet life is here too. Peculiar sea cucumbers drifting across the sediment, polychaete worms, amphipods, tiny crustaceans that are remarkably hardy and remarkably everywhere. Scientists drop baited cameras to the seafloor in the abyssal zone, and within hours the frame is crawling with life. Life down here is not thriving in the way we think of thriving. It is slow, careful, and deeply patient. But it is there. And then, beneath even the abyss, there are the trenches. The hadal zone, named after Hades, the Greek underworld. These are the deepest parts of the ocean, mostly found where tectonic plates collide and one slides beneath the other. It's here, in the Mariana Trench and the few other hadal trenches we've managed to study, that the ocean reaches its most extreme depths, and even here there is life. In 2023, scientists filming in the Izu Ogasawara Trench off the coast of Japan captured something extraordinary on a baited camera, a small, pale, almost translucent juvenile snailfish drifting through the darkness at a depth of 8,336 meters. It is now the deepest fish ever recorded alive, a creature so small you could hold it in your hand, surviving in the most hostile environment on the planet, utterly unbothered. Now I want to tell you about a discovery that fundamentally changed the way scientists think about life, not just on Earth, but potentially across the entire universe. In 1977, a team of scientists aboard a deep-sea submersible called Alvin descended to a spot on the seafloor in the eastern Pacific Ocean, near the Galapagos Islands. They were looking for hydrothermal vents, cracks in the seafloor where geothermal heat from inside the Earth was expected to warm the surrounding water. What they found was something nobody had predicted. Clustered around these vents in water that reached temperatures of up to 400 degrees Celsius and was full of toxic chemicals was an explosion of life. Tube worms over 2 meters long, giant white clams, pale crabs swarming everywhere, shrimp and mussels and fish, all living in complete darkness, with no sunlight, far from any surface-based food source. Up until this moment, every single ecosystem we had ever studied on Earth was ultimately powered by one thing: sunlight. Plants absorb it. Animals eat the plants. Other animals eat those animals. Sunlight was the foundation of every food chain we knew. These creatures weren't doing that. They were living off chemosynthesis, bacteria that extract energy from the chemical reactions between the hot vent fluid and the cold seawater. The tube worms, for instance, have no mouth and no stomach. They absorb the bacteria directly into their bodies and let the bacteria do the work of converting chemicals into energy. This was a completely alien way of being alive. And it was happening right here on Earth. The implications took a while to sink in, but they were enormous. If life can survive and thrive with no sunlight, no photosynthesis, no connection to the surface world, just heat and chemistry, then the list of places in the universe where life might exist just got dramatically longer. Europa, one of Jupiter's moons, has a thick shell of ice covering what is believed to be a liquid water ocean. That ocean is kept liquid by tidal heating from Jupiter's gravity, not by sunlight. Enceladus, one of Saturn's moons, is literally spraying water vapor and ice out into space from hydrothermal vents beneath its own frozen surface. Before 1977, those moons were interesting. After 1977, they became genuinely exciting. The deep ocean didn't just reveal a hidden world beneath our feet. It expanded the entire map of where life in the universe could be hiding. Here's the thing about the deep ocean. Every time we send something down there, we find something we weren't expecting. Every single time. The giant squid was considered a myth, a sea monster from sailors' tales, until a live one was finally photographed in 2004 and filmed in 2006. Before that, everything we knew about it came from dead specimens washed ashore or pulled up in fishing nets. An animal the size of a school bus, one of the largest invertebrates on Earth, managed to avoid being caught on camera until the 21st century. It was hiding in the deep ocean. Scientists have discovered new species of whale from their sounds alone, picking up songs in the deep ocean from creatures that hadn't been formally documented. We found deep-sea coral gardens that are thousands of years old. We've discovered microbes living inside the seafloor rock itself, deep beneath even the ocean floor, in conditions that would sterilize anything we know from the surface world. In 2023, a research expedition surveying a stretch of seafloor off the coast of Chile came back with descriptions of over 100 new species from a single dive series: sponges, corals, sea stars, worms, creatures nobody had ever seen or named. This is not ancient history. This is last year. And the uncomfortable flip side of all this wonder is what we're doing to a place we don't even understand yet. Deep sea trawling, a fishing method that drags enormous weighted nets across the seafloor, destroys ancient coral structures that took centuries to grow. It flattens ecosystems we haven't even cataloged. It's estimated that bottom trawling disturbs more seafloor per year than any other human activity on Earth, more than all terrestrial construction combined. Noise pollution from shipping and sonar affects creatures that navigate and communicate by sound in a world where sound is the primary sense. Light pollution from offshore drilling disrupts the bioluminescent signals animals use to survive. And now, looming on the horizon is deep-sea mining. The seafloor in certain regions is covered with what are called polymetallic nodules, potato-sized rocks, rich in cobalt, manganese, nickel, and other minerals that are in high demand for electric car batteries and electronics. Mining companies have their eyes on them. The debate over whether to mine them is happening right now in international waters, with regulatory bodies that are only just being established. The worry among scientists is that we would be permanently destroying ecosystems, ones that took millions of years to develop in places we've barely seen, for resources we may or may not actually need in the long run. It's a complicated conversation, but it's one that's hard to have properly when we don't even know what's down there. Here's where things get genuinely exciting, because the tools we have for exploring the deep ocean are advancing faster than at any point in history. Autonomous underwater vehicles, AUVs, can now be programmed to dive to the seafloor, map it with sonar, and return without any human involvement. They're cheaper than manned submersibles, they can stay down longer, and they can cover far more ground. A new generation of these robots can operate in the deepest parts of the ocean, withstanding pressures that would reduce a conventional submarine to scrap metal. Fiber optic hydrophones, essentially underwater microphones, are being laid across the seafloor to listen to the ocean. They're picking up whale songs, submarine geological activity, distant earthquakes. They're turning the whole ocean floor into a listening station. There are also projects working on using satellite data to infer what's beneath the surface, measuring tiny gravitational variations in the ocean caused by underwater mountains and trenches, and using those measurements to build maps. It's not as good as actually sending something down, but it's revealing structure we didn't know existed. Perhaps most exciting is the increasing use of environmental DNA, eDNA. Seawater contains traces of DNA shed by every creature that has passed through it. By filtering and analyzing water samples from different ocean depths, scientists can now build a picture of what species are present even without ever seeing them directly. A water sample from 3,000 meters deep can tell you what was swimming nearby within hours or days. It's like taking a census without the door-to-door visits. We are at a genuinely historic moment in ocean exploration. The tools are arriving. The funding, slowly, is following. And the discoveries are accelerating. You might be sitting there thinking, okay, this is all interesting, but I'm not a marine biologist. I live nowhere near the ocean. Why does any of this actually matter to me? Fair question. Here's the answer. The deep ocean regulates the climate of the planet you live on. Deep ocean currents, driven by differences in temperature and salinity, move heat around the globe in a way that determines what the weather looks like in London, New York, Mumbai, and everywhere else. These currents are sometimes called the ocean conveyor belt, and they are one of the primary reasons that life on the surface of this planet is as stable as it has been. The deep ocean is also an enormous carbon sink. It absorbs carbon dioxide from the atmosphere and stores it in the deep water and in the sediment at the bottom. When marine life in the upper ocean dies, it sinks, carrying the carbon it has absorbed down into the deep, where it can be stored for centuries or millennia. This process is called the biological pump, and it is one of the major reasons that the Earth's atmosphere has maintained conditions suitable for complex life for as long as it has. Disturb the deep ocean? Warm it too much? Acidify it too much? Strip it of its life? And you disturb those processes. The consequences aren't abstract. They're felt in the air you breathe and the weather outside your window. The deep ocean is also where the next generation of medicines may come from. Creatures that have evolved in extreme conditions produce extraordinary biochemistry. Compounds derived from deep-sea organisms are already being studied for potential treatments for cancer and bacterial infections. We have barely scratched the surface of what the pharmacological library of the deep sea might contain. The deep ocean isn't just interesting, it's fundamental. It's the life support system for the planet, and we barely know how it works. Here is what I keep coming back to when I think about the deep ocean. We live on a water world. From space, the Earth is unmistakably blue. Oceans cover nearly 3/4 of its surface. And we have sailed on those oceans for thousands of years, fished them, dumped our waste into them, built our civilizations on their edges, and we still don't know what most of it looks like. There is something both humbling and genuinely thrilling about that. In a world that sometimes feels completely mapped and cataloged and photographed and known, there are still places on Earth, real places that no human eye has ever seen. Creatures alive right now, in the dark miles beneath the surface, that have never been named. Ecosystems that have existed for millions of years that we have not yet discovered. We went to the moon. We sent probes to the edge of the solar system. We built telescopes that can see the first light of the universe. And the deepest, strangest, most alien world on Earth is right here, beneath the waves. We just haven't looked yet.